Section 12 of My Inventions and Other Works of Nikola Tesla, Electrical Experimenter, February to October 1919. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com. The Moon's Rotation by Nikola Tesla, Part 1. This article was published in Electrical Experimenter, April 1919. Since the appearance of my article entitled The Famous Scientific Illusions in your February issue, I have received a number of letters criticizing the views I expressed regarding the Moon's axial rotation. These have been partly answered by any statement to the New York Tribune of February 23rd, which allow me to quote: "In your issue of February 2nd, Mr. Charles E. Manier, commenting upon my article in the Electrical Experimenter for February, which appeared in the Tribune of January 26, suggests that I give a definition of axial rotation. I intend to be explicit on this point, as may be judged from the following quotation. The unfailing test of the spinning of a mass is, however, the existence of energy of motion. The Moon is not possessed of such vis viva. By this I meant that axial rotation is not simply rotation upon an axis nonchalantly defined in dictionaries, but is a circular motion in the true physical sense. That is, one in which half the product of the mass with the square of velocity is a definite and positive quantity. The Moon is a nearly spherical body of a radius of about 1,087.5 miles, from which I calculate its volume to be approximately 5,300,216,300 cubic miles. Since its mean density is 3.27, 1 cubic foot of material composing it weighs close on 205 pounds. Accordingly, the total weight of the satellite is about 79,969 trillion, and its mass 2,483,500 terrestrial short tons. Assuming that the Moon does physically rotate upon its axis, it performs one revolution in 27 days, 7 hours, 43 minutes, and 11 seconds, or 2,360,591 seconds. If, in conformity with mathematical principles, we imagine the entire mass concentrated at a distance from the center equal to 2/5 of the radius, then the calculated rotational velocity is 3.04 feet per second, at which the globe would contain 11,474 billion short foot tons of energy, sufficient to run 1 billion horsepower for a period of 1,323 years. Now I say that there is not enough of that energy in the Moon to run a delicate watch. In astronomical treatises, usually the argument is advanced that if the lunar globe did not turn upon its axis, it would expose all parts to terrestrial view. As only a little over 1/2 is visible, it must rotate. But this inference is erroneous, for it only admits one alternative. There are an infinite number of axes besides its own, in each of which the Moon might turn, and still exhibit the same peculiarity. I have stated in my article that the Moon rotates about an axis passing through the center of the Earth, which is not strictly true, but it does not vitiate the conclusions I have drawn. It is well known, of course, that the two bodies revolve around a common center of gravity, which is at a distance of a little over 2,899 miles from the Earth's center. Another mistake in books on astronomy is made in considering this motion equivalent to that of a weight whirled on a string or in a sling. In the first place, there is an essential difference between these two devices, though involving the same mechanical principle. If a metal ball attached to a string is whirled around and the latter breaks, an axial rotation of the missile results, which is definitely related in magnitude and direction to the motion preceding. By way of illustration, if the ball is whirled on the string clockwise 10 times per second, then when it flies off, it will rotate on its axis 10 times per second, likewise in the direction of a clock. Quite different are the conditions when the ball is thrown from a sling. In this case, a much more rapid rotation is imparted to it in the opposite sense. There is no true analogy to these in the motion of the moon. If the gravitational string, as it were, would snap, the satellite would go off in a tangent without the slightest swerving or rotation, for there is no moment about the axis, and consequently no tendency whatever to spinning motion. Mr. Manière is mistaken in his surmise as to what would happen if the earth were suddenly eliminated. Let us suppose that this would occur at the instant when the moon is in opposition. Then it would continue on its elliptical path around the sun, presenting to it steadily the face which was always exposed to the earth. If, on the other hand, the latter would disappear at the moment of conjunction, the moon would gradually swing around through 180 degrees, and after a number of oscillations, revolve again with the same face to the sun. In either case there would be no periodic changes, but eternal day and night, respectively, on the sides turned towards and away from the luminary. Some of the arguments advanced by the correspondents are ingenious, and not a few comical. None, however, are valid. One of the writers imagines the earth in the center of a circular orbital plate, having fixedly attached to its peripheral portion a disc-shaped moon, in frictional or geared engagement with another disc of the same diameter, and freely rotatable on a pivot projecting from an arm entirely independent of the planetary system. The arm being held continuously parallel to itself, the pivoted disc, of course, is made to turn on its axis as the orbital plate is rotated. This is a well-known drive, and the rotation of the pivoted disc is as palpable a fact as that of the orbital plate. But the moon in this model only revolves about the center of the system, without the slightest angular displacement on its own axis. The same is true of a cartwheel to which this writer refers. So long as it advances on the earth's surface, it turns on the axle in the true physical sense. When one of its spokes is always kept in a perpendicular position, the wheel revolves around the earth's center, but axial rotation has ceased. Those who think that it then still exists are laboring under an illusion. An obvious fallacy is involved in the following abstract reasoning. The orbital plate is assumed to gradually shrink, so that finally the centers of the earth and the satellite coincide when the latter revolves simultaneously about its own and the earth's axis. We may reduce the earth to a mathematical point, and the distance between the two planets to the radius of the moon without affecting the system in principle. But a further diminution of the distance is manifestly absurd and of no bearing on the question under consideration. In all the communications I have received, though different in the manner of presentation, the successive changes of position in space are mistaken for axial rotation. So, for instance, a positive refutation of my arguments is found in the observation that the moon exposes all sides to other planets. It revolves, to be sure, but none of the evidences is a proof that it turns on its axis. Even the well-known experiment with the Foucault pendulum, although exhibiting similar phenomena as on our globe, would merely demonstrate a motion of the satellite about some axis. The view I have advanced is not based on a theory, but on facts, demonstrable by experiment. It is not a matter of definition as some would have it. A mass revolving on its axis must be possessed of momentum. If it has none, there is no axial rotation, all appearances to the contrary notwithstanding. A few simple calculations based on well-established mechanical principles will make this clear. Consider the first case of two equal weights, W and WS, in Figure 1, whirled about the center 0 on a string S as shown. Assuming the latter to break at A, both weights will fly off on tangents to their circles of gyration, and being animated with different velocities, they will rotate around their common center of gravity, 0. If the weights are whirled n times per second, then the speed of the outer and the inner one will be respectively v equals 2 times r plus small r, n, and v equals 2 pi times r minus r, n, and the difference v minus v squared equals 4 pi times r times n will be the length of the circular path of the outer weight. Inasmuch, however, there will be equalization of the speeds until the mean value is attained, we shall have v minus v1 divided by 2 equals 2 pi rn equals 2 pi r large N being the number of revolutions per second of the weights around their center of gravity. Evidently, then, the weights continue to rotate at the original weight and in the same direction. I know this to be a fact from actual experiments. It also follows that a ball, as that shown in the figure, will behave in a similar manner, for the two half-spherical masses can be concentrated at their centers of gravity, and M and M1 respectively will be at a distance from 0 equal to 3/8 times r. This being understood, imagine a number of balls M carried by as many spokes S, radiating from a hub H, as illustrated in Figure 2, and let this system be rotated n times per second around center 0 on frictionless bearings. A certain amount of work will be required to bring the structure to this speed, and it will be found that it equals exactly half the product of the masses with the square of the tangential velocity. Now, if it be true that the moon rotates in reality on its axis, this must also hold good for each of the balls, as it performs the same kind of movement. Therefore, imparting to the system a given velocity, energy must have been used up in the axial rotation of the balls. Let m be the mass of one of these, and r the radius of gyration. Then the rotational energy will be E equals 1/2 m times 2 pi Rn squared, since for one complete turn of the wheel every ball makes one revolution on its axis. According to the prevailing theory, the energy of axial rotation of each ball will be C equals 1/2 m 2 pi Rn squared, R1 being the radius of gyration about the axis, and equal to 0.6325 r. We can use as large balls as we like, and so make C a considerable percentage of E, and yet it is positively established by experiment that each of the rotating balls contain only the energy E, no power whatever being consumed in the supposed axial rotation, which is consequently wholly illusionary. Something even more interesting may, however, be stated. As I have shown before, a ball flying off will rotate at the rate of the wheel and in the same direction. But this whirling motion, unlike that of a projectile, neither adds to nor detracts from the energy of the translatory movement, which is exactly equal to the work consumed in giving to the mass the observed velocity. From the foregoing it will be seen that in order to make one physical revolution on its axis, the moon should have twice its present angular velocity, and then it would contain a quantity of stored energy as given in my above letter to the New York Tribune, on the assumption that the radius of gyration is 2/5 that of figure. This, of course, is uncertain, as the distribution of density in the interior is unknown. But from the character of motion of the satellite, it may be concluded with certitude that it is devoid of momentum about its axis. If it be bisected by a plane tangential to the orbit, the masses of the two halves are inversely as the distances of their centers of gravity from the Earth's center, and therefore if the latter were to disappear suddenly, no axial rotation as in the case of a weight thrown off, would ensue. End of section 12. Read by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. Section 13 of My Inventions and Other Works of Nikola Tesla, Electrical Experimenter, February to October 1919. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. The Moon's Rotation, Part 2, by Nikola Tesla. This article was published in Electrical Experimenter, June 1919. In revising my article on the Moon's rotation, which appeared in the April issue of the Electrical Experimenter, I appended a few remarks to the original text in further support and elucidation of the theory advanced. Due to the printer's error, these were lost, and in consequence I found it necessary to forward another communication, which unfortunately was received too late for embodiment in the May number. Meanwhile, many letters have reached me in which certain phenomena represented by rotating bodies, as the Moon's librations of longitude, are cited as evidences of energy due to spinning motion. In revising my article on the Moon's rotation, which appeared in the April issue of the Electrical Experimenter, I appended a few remarks to the original text in further support and elucidation of the theory advanced. Due to the printer's error, these were lost, and in consequence I found it necessary to forward another communication, which unfortunately was received too late for embodiment in the May number. Meanwhile, many letters have reached me in which certain phenomena presented by rotating bodies, as the Moon's librations of longitude, are cited as evidences of energy due to spinning motion, i.e., proofs of axial rotation of the satellite in the true physical sense. I trust that the following amplified statement will meet all of the objections raised, and convert to my views those who are still unconvinced. The kinetic energy of a rotating mass can be determined in 4 ways, which are illustrated in diagrams, figures 1, 2, 3, and 4, and may be found more or less suitable. Referring to Figure 1, the method consists in selecting judiciously a number of points, as O1, O2, O3, etc., within the straight rod or mass M, respectively at distances r1, r2, r3, etc., from the axis of rotation 0, and calculating the square root of the mean square of these distances, its value being rg, denoted radius of gyration. The effective velocity of the mass at n revolutions per second will be v e equals 2 pi r g n, and its kinetic energy E equals half m times v e squared equals half m times 2 pi r g n squared. In Figure 2, the mass m, rotating n times per second, about an axis 0 at right angles to the plane of the paper. In Figure 2, the mass m, rotating n times per second, about an axis 0 at right angles to the plane of the paper, is divided into numerous elements or small parts, most conveniently very thin concentric laminae, as 1, 1, 1, 2, 1, 3, etc., at distances r1, r2, r3, etc., from 0. Since the kinetic energy of each part is equal to half the product of its mass and the square of the velocity, the sum of all these elemental energies, E equals half mv2 equals half m1, v1 2 plus 1 half m2, v2 squared plus 1 half ma v squared 3 plus equals half m1 times 2 pi r1n squared plus half m2 times 2 pi r squared n squared plus 1 half ms 2 pi r3n squared. A different form of expression for the energy of a rotating body may be obtained by determining its moment of inertia. For this purpose the mass m in Fig. 3, rotating n times per second about an axis O, is separated into minute parts as m1, m2, m3, etc., respectively at distances r1, r2, r3, etc., from the same. The sum of the products of all these small masses and the squares of their distances is the moment of inertia I, and then E equals 1/2 I W2, W equals 2 pi n, being the angular velocity. It is obvious that in all these instances many points or elements will be required for great accuracy, but as a rule very few are sufficient in practice. Still another way to compute the kinetic energy is illustrated in Fig. 4, in which case quantity I is given in terms of the moment of inertia IC about another axis parallel to 0 and passing through the center of gravity C of mass m. In conformity with this, the energy of motion E equals half mv squared plus half IE w squared, in which equation v is the velocity of the center of gravity. The preceding is deemed indispensable, as I note that the correspondents, even those who seem thoroughly familiar with mechanical principles, fail to make a distinction between theoretical and physical truths, which is essential to my argument. In estimating the kinetic energy of a rotating mass in any of the ways indicated, we arrive, through suitable conceptions and methods of approximation, at expressions which may be made quantitatively precise to any desired degree, but do not truly define the actual condition of the body. To illustrate, when proceeding according to the plan of Fig. 1, we find a certain hypothetical velocity with which the entire mass should move in order to contain the same energy, a state wholly imaginary and irreconcilable with the actual. Only when all particles of the body have the same velocity does the product 1/2 mv squared specify a physical fact and is numerically and descriptively accurate. Still more remote from palpable truth is the equation of motion obtained in the manner indicated in Fig. 4, in which the first term represents the kinetic energy of translation of the body as a whole, and the second that of its axial rotation. The former would demand a movement of the mass in a definite path and direction, all particles having the same velocity, the latter its simultaneous motion in another path and direction, the particles having different velocities. This abstract idea of angular motion is chiefly responsible for the illusion of the moon's axial rotation, which I shall endeavor to dispel by additional evidences. With this object, attention is called to Fig. 5, showing a system composed of 8 balls M, which are carried on spokes S, radiating from a hub H, rotatable around a central axis 0 in bearings supposed to be frictionless. It is an arrangement similar to that before illustrated, with the exception that the balls, instead of forming parts of the spokes, are supported in screw pivots, which are normally loose but can be tightened so as to permit both free turning and rigid fixing as may be desired. To facilitate observation, the spokes are provided with radial marks and the lower sides of the balls are shaded. Assume first that the drawing depicts the state of the rest, the balls being rotatable without friction, and let an angular velocity, W equals 2 pi n, be imparted to the system in the clockwise direction, as indicated by the long solid arrow. Viewing a ball as M, its successive positions 1, 2, 3 to 8 in space, and also relatively to the spoke, will be just as drawn, and it is evident from an inspection of the diagram that while moving with the angular velocity W about 0 in the clockwise direction, the ball turns with respect to its axis, at the same angular velocity but in the opposite direction, that of the dotted arrow. The combined result of these two motions is a translatory movement of the ball, such that all particles are animated with the same velocity v, which is that of its center of gravity. In this case, granted that there is absolutely no friction, the kinetic energy of each ball will be given by the product of 1/2 m times v squared, not approximately, but with mathematical rigor. If now the pivots are screwed tight and the balls fixed rigidly to the spokes, this angular motion relatively to their axis becomes physically impossible, and then it is found that the kinetic energy of each ball is increased, the increment being exactly the energy of rotation of the ball on its axis. This fact, which is borne out both by theory and experiment, is the foundation of the general notion that a gyrating body, in this instance ball M, presenting always the same face towards the center of motion, actually rotates upon its axis in the same sense, as indicated by the short full arrow. But it does not, though to the eye it seems so. The fallacy will become manifest on further inquiry. To begin with, observe that when a mass, say the armature of an electric motor, rotating with the angular velocity w is reversed, its speed is minus w, and the difference w minus times minus w equals 2 times w. Now, in fixing the ball to the spoke, the change of angular velocity is only w. Therefore, an additional velocity w would have to be imparted to it in order to cause a clockwise rotation of the ball on its axis in the true significance of the word. The kinetic energy would then be equal to the sum of the energies of the translatory and axial motions, not merely in the abstract mathematical meaning, but as a physical fact. I am well aware that, according to the prevailing opinion, when the ball is free on the pivots, it does not turn on its axis at all, and only rotates with the angular velocity of the frame when rigidly attached to the same. But the truth will appear upon a closer examination of this kind of movement. Let the system be rotated as first assumed and illustrated, the balls being perfectly free on the pivots, and imagine the latter to be gradually tightened to cause friction, slowly reducing and finally preventing the slip. At the outset, all particles of each ball have been moving with the speed of its center of gravity, but as the bearing resistance asserts itself more and more, the translatory velocity of the particles nearer to the axis 0 will be diminishing, while that of the diametrically opposite ones will be increasing, until the maxima of these changes are attained, when the balls are firmly held. In this operation we have thus deprived those parts of the masses which are nearer to the center of motion of some kinetic energy of translation, while adding to the energy of those which are farther, and obviously the gain was greater than the loss, so that the effective velocity of each ball as a whole was increased. Only so have we augmented the kinetic energy of the system, not by causing axial rotation of the balls. The energy E of each of these is solely that of translatory movement, with an effective velocity VE as above defined, such that E equals half mv squared. The axial rotations of the ball in either direction are but apparent. They have no reality whatever and call for no mechanical effort. It is merely when an extraneous force acts independently to turn the whirling body on its axis that energy comes into play. Incidentally, it should be pointed out that in true axial rotation of a rigid and homogeneous mass, all symmetrically situated particles contribute equally to the momentum, which is not the case here. That there exists not even the slightest tendency to such motion can, however, be readily established. For this purpose I would refer to Figure 6, showing a ball M of radius r, the center C of which is at a distance r from axis 0, and which is bisected by a tangential plane PP as indicated, the lower half sphere being shaded for distinction. The kinetic energy of the ball, when whirled n times per second, about zero, is, according to the first form of expression, E equals half mv e squared equals half m times 2 pi r g n squared, m being the mass and r g the radius of gyration. But, as explained in connection with Figure 4, we have also E equals 1 half mv squared plus 1 half IEW squared, v equals 2 pi r n being the velocity of the center of gravity, c, and IC, the moment of inertia of the ball, about the parallel axis passing through c, and equal to 2/5 mi squared, so that E equals half m times 2 pi r n squared, plus half m r squared times 2 pi n squared. Neither of these two expressions for E describes the actual state of the body, but the first is certainly preferable, conveying, as it does, the idea of a single motion instead of two, one of which, moreover, is devoid of existence. I shall first undertake to demonstrate that there is no torque or rotary effort about center C, and that the kinetic energy of the supposed axial rotation of the ball is mathematically equal to zero. This makes it necessary to consider the two halves separated by the tangential plane PP, wholly independent from one another. Let C1 and C2 be their centers of gravity. Then CC1 equals CC2 equals 3/8 r. In order to ascertain the kinetic energy of the hemispheres, we have to find their radii of gyration, which can be done by determining the moments of inertia IC1 and IC2 about parallel axes passing through C1 and C2. Complex calculation will be avoided by remembering that the moment of inertia of either one of the half spheres about an axis through C is IC equals 1 half mr squared, and since m equals 2m, IC equals 2/5 mr squared. This can be expressed in terms of the moments IC1 and IC2, namely IC equals IC1 plus m times 3/8 r squared equals IC2 plus m times 3/8 r squared. Hence IC1 equals IC2 equals IC minus m times 3/8 r squared equals 2/5 m times r squared minus 9/64 m times r squared equals 83/320 m times r squared. Following the same rule, the moments of inertia of the half spheres about the axis passing through the center of motion 0 can be found. Designating the moments for the upper and lower halves of the ball, respectively, IO1 and IO2, we have IO1 equals m times r plus 3/8 r squared, plus IC1 equals m times r plus 3/8 r squared, plus 83/320 m times r squared, and IO squared equals m times r minus 3/8 r squared, plus IC squared equals m times r minus 3/8 r squared, plus 83/320 m r squared. Thus, for the upper half sphere, the radius of the gyration, rg1, equals IO1 divided by m equals r plus 3/8 r squared plus 83/320 r squared. And for the lower one, rg2 equals IO2 divided by m equals r minus 3/8 r squared plus 83/320 r squared. These are the distances from the center, 0, at which the masses of the half spheres may be concentrated, and then the algebraic sum of their energies, which are wholly translatory, those of axial rotation being nil, will be exactly equal to the total kinetic energy of the ball as a unit. The significance of this will be understood by reference to Figure 7, in which the two masses, condensed into points, are represented as attached to independent weightless strings of lengths rg1 and rg2, which are purposely shown as displaced, but should be imagined as coincident. It will be readily seen that if both strings are cut in the same instant, the masses will fly off in tangents to their circular orbits, the angular movement becoming rectilinear, without any transformation of energy occurring. Let us now inquire what will happen if the two masses are rigidly joined, the connection being assumed imponderable. Here we come to the real bug in the question under discussion. Evidently, so long as the whirling motion continues, and both the masses have precisely the same angular velocity, this connecting link will be of no effect whatever. Not the slightest turning effort about the common center of gravity of the masses, or tendency of equalization of energy between them will exist. The moment the strings are broken and they are thrown off, they will begin to rotate, but as pointed out before, this motion neither adds to or detracts from the energy stored. The rotation is, however, not due to an exclusive virtue of angular motion, but to the fact that the tangential velocities of the masses, or parts of the body thrown off, are different. To make this clear and to investigate the effects produced, imagine two rifle barrels, as shown in Figure 8, placed parallel to each other with their axes separated by a distance, Rg1 minus Rg2, and assume that two balls of the same diameter, each having mass m, are discharged with muzzle velocities v1 and v2 respectively equal to 2 pi n Rg1 and 2 pi n Rg2, as in the case just considered. If it be further supposed that at the instant of leaving the barrels, the balls are joined by a rigid but weightless link, they will rotate about their common center of gravity, and in accordance with the statement in my previous article above mentioned, the relation will exist v1 minus v2 divided by 2 equals pi n times Rg1 minus Rg2, n being the number of revolutions per second. The equalization of the speeds and kinetic energies of the balls will be, under these circumstances, very rapid, but in two heavenly bodies linked by gravitational attraction, the process might require ages. Now, this whirling movement is real and requires energy, which obviously must be derived from that originally imparted, and consequently must reduce the velocity of the balls in the direction of flight by an amount which can be easily calculated. At the moment of discharge, the total kinetic energy was E equals half m v1 squared plus half m v2 squared, which is evidently equal to mv3 squared, v3 being the effective velocity of the common center of gravity, from which follows that v3 equals v1 squared plus v2 squared divided by 2. The speed of revolution of the masses is, of course, v1 minus v2 divided by 2, and the rotational energy of both balls, which must be considered as points, is E equals m times v1 minus v2, m times v1 minus v2 divided by 2. The kinetic energy of translation in the direction of flight, then, is 1/2 m v1 squared plus 1/2 m v2 squared minus m times v1 minus v2 divided by 2 equals m times v1 plus v2 divided by 2 equals m v4 squared. v4 equals v1 plus v2 divided by 2, being the speed of the common center of gravity, so that v3 minus v4 is the loss of velocity in the direction of flight, owing to the rotation of the two mass points. If instead of these we would deal with the balls as they are, their rotational energy E1 equals E plus I W squared equals m times v1 plus v2 divided by 2 plus I times 2 pi n squared, I being the moment of inertia of each ball about its axis. As will be seen, we arrive at precisely the same result, whether the movement is rectilinear or in a circle. In both cases, the total kinetic energy can be divided into two parts, respectively, of the same numerical values. But there is an essential difference. In angular motion, the axial rotation is nothing more than an abstract conception. In rectilinear movement, it is a positive event. Virtually all satellites rotate in like manner, and the probability that the acceleration or retardation of their axial motions, if they ever existed, should come to a stop precisely at a definite angular velocity, is infinitesimal, while it is almost absolutely certain that all movement of this kind would ultimately cease. The most plausible view is that no true moon has ever rotated on its axis, for at the time of its birth there must have been some deformation and displacement of its center of gravity through the attractive force of the mother planet, so as to make its peculiar position in space, relative to the latter, in which it persists irrespective of distance, more or less stable. In explanation of this, suppose that one of the balls, as M in Fig. 5, is not of homogeneous material, and that it is similarly supported but on an axis passing through its center of gravity, instead of form. Then, no matter in what position the ball is fixed on the pivots, its kinetic energy and centrifugal pull will be the same. Nevertheless, a directive tendency will exist, as the two centers do not coincide, and there is consequently no dynamic balance. When permitted to turn freely on the axis of gravity, the body, of whatever shape it may be, will tend to place itself so that the line joining the two center points to zero, and there may be two positions of stability, but generally, if the center of gravity is not greatly displaced, the heavier side will swing outwardly. Such condition may obtain in the moon if it had solidified before receding from the earth to great distance, when the arrangement of the masses in its interior became subject to gravitational forces of its own, vastly greater than the terrestrial. It has been suggested that the planet is egg-shaped or ellipsoidal, but the departure from spherical form must be inconsiderable. It may even be a perfect sphere with the centers of gravity and symmetry coinciding, and still rotate as it does. Whatever be its origin and past history, the fact is that at present all parts have the same angular velocity, as though it were rigidly connected with the earth. This state must endure forever unless forces from without the luna-terrestrial system bring about different conditions, and thus the hope of the star-gazers that its other side may become visible some day must be indefinitely deferred. A motion of this character, as I have shown, precludes the possibility of axial rotation. The easiest way to free ourselves of this illusion is to conceive the satellite subdivided into minute and entirely independent parts, as dust particles, which have different orbital but rigorously the same angular velocities. One must at once recognize that the kinetic energy of such an agglomeration is solely translational, there being absolutely no tendency to axial rotation. This makes it also perfectly clear why the moon, provided its distance does not greatly increase, must always turn the same face to us, even without any inherent tendency nor so much as the slightest effort from the earth. Referring to the librations of longitude, I do not see that they have any bearing on this question. In astronomical treatises, the axial rotation of the moon is accepted as a material fact, and it is thought that its angular velocity is constant, while that of the orbital movement is not, thus resulting in an apparent oscillation, revealing more of its surface to our view. To a degree this may be true, but I hold that the mere change of orbital velocity, as will be evident from what has been stated before, could not produce these phenomena, for no matter how fast or slow the gyration, the position of the body relative to the center of attraction remains the same. The real cause of these axial displacements is the changing distance of the moon from the earth, owing to which the tangential components of velocity of its parts are varied. In apogee, when the planet recedes, the radial component of velocity decreases, while the tangential increases, but as the decrement of the former is the same for all parts, this is more pronounced in the regions facing the earth than in those turning away from it, the consequence being an axial displacement exposing more of the eastern side. In perigee, on the contrary, the radial component increases, and the effect is just the opposite, with the result that more of the western side is seen. The moon actually swings on the axis, passing through its center of gravity, on which it is supported like a ball on a string. The forces involved in these pendular movements are incomparably smaller than those required to effect changes in orbital velocity. If we estimate the radius of gyration of the satellite at 600 miles and its mean distance from the Earth at 240,000 miles, then the energy necessary to rotate it once a month would be only 600 divided by 240,000 squared equals 1 divided by 160,000 of the kinetic energy of the orbital movement. End of section 13. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com.
Section 14 of my Inventions and Other Works of Nikola Tesla, Electrical Experimenter, February to October 1919. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Electrical Oscillators by Nikola Tesla. This article was published in Electrical Experimenter, July 1919. Few fields have been opened up the exploration of which has proved as fruitful as that of high-frequency currents. The singular properties and the spectacular character of the phenomena they presented immediately commanded universal attention. Scientific men became interested in their investigation. Engineers were attracted by the commercial possibilities, and physicians recognized in them a long-sought means for effective treatment of bodily ills. Since the publication of my first researches in 1891, hundreds of volumes have been written on the subject, and many invaluable results obtained through the medium of this new agency. Yet the art is only in its infancy, and the future has incomparably bigger things in store. From the very beginning, I felt the necessity of producing efficient apparatus to meet a rapidly growing demand, and during the 8 years succeeding my original announcement, I developed not less than 50 types of these transformers or electrical oscillators, each complete in every detail and refined to such a degree that I could not materially improve any of them today. Had I been guided by practical considerations, I might have built up an immense and profitable business, incidentally rendering important services to the world. But the force of circumstances and the ever-enlarging vista of greater achievements turned my efforts in other directions. And so it comes that instruments will shortly be placed on the market which, oddly enough, were perfected 20 years ago. These oscillators are expressly intended to operate on direct and alternating lighting circuits, and to generate damped and undamped oscillations or currents of any frequency, volume, and tension within the widest limits. They are compact, self-contained, require no care for long periods of time, and will be found very convenient and useful for various purposes, as wireless telegraphy and telephony, conversion of electrical energy, formation of chemical compounds through fusion and combination, synthesis of gases, manufacture of ozone, lighting, welding, municipal, hospital and domestic sanitation and sterilization, and numerous other applications in scientific laboratories and industrial institutions. While these transformers have never been described before, the general principles underlying them were fully set forth in my published articles and patents, more particularly those of September 22, 1896, and it is thought, therefore, that the appended photographs of a few types, together with a short explanation, will convey all the information that may be desired. The essential parts of such an oscillator are a condenser, a self-induction coil for charging the same to a high potential, a circuit controller, and a transformer which is energized by the oscillatory discharges of the condenser. There are at least 3, but usually 4, 5 or 6 circuits in tune, and the regulation is effected in several ways, most frequently merely by means of an adjusting screw. Under favorable conditions, an efficiency as high as 85% is attainable. That is to say, that percentage of the energy supplied can be recovered in the secondary of the transformer. While the chief virtue of this kind of apparatus is obviously due to the wonderful powers of the condenser, special qualities result from concatenation of circuits under observance of accurate harmonic relations, and minimization of frictional and other losses, which has been one of the principal objects of the design. Broadly, the instruments can be divided into two classes: one in which the circuit controller comprises solid contacts, and the other in which the make and break is effected by mercury. Figures 1 to 8 inclusive belong to the first, and the remaining ones to the second class. The former are capable of an appreciably higher efficiency on account of the fact that the losses involved in the make and break are reduced to the minimum and the resistance component of the damping factor is very small. The latter are preferable for purposes requiring larger output and a great number of breaks per second. The operation of the motor and circuit controller of course consumes a certain amount of energy, which, however, is the less significant the larger the capacity of the machine. In Figure 1 is shown one of the earliest forms of oscillator constructed for experimental purposes. The condenser is contained in a square box of mahogany, upon which is mounted the self-induction or charging coil wound, as will be noted in two sections connected in multiple or series according to whether the tension of the supply circuit is 110 or 220 volts. From the box protrude four brass columns carrying a plate with the spring contacts and adjusting screws, as well as two massive terminals for the reception of the primary of the transformer. Two of the columns serve as condenser connections, while the other pair is employed to join the binding posts of the switch in front to the self-inductance and condenser. The primary coil consists of a few turns of copper ribbon, to the ends of which are soldered short rods fitting into the terminals referred to. The secondary is made in two parts, wound in a manner to reduce as much as possible the distributed capacity and at the same time enable the coil to withstand a very high pressure between its terminals at the center, which are connected to binding posts on two rubber columns projecting from the primary. The circuit connections may be slightly varied, but ordinarily they are as diagrammatically illustrated in the electrical experimenter for May on page 89, relating to my oscillation transformer photograph, of which appeared on page 16 of the same number. The operation is as follows. When the switch is thrown on, the current from the supply circuit rushes through the self-induction coil, magnetizing the iron core within and separating the contacts of the controller. The high tension-induced current then charges the condenser, and upon closure of the contacts, the accumulated energy is released through the primary, giving rise to a long series of oscillations which excite the tuned secondary circuit. This device has proved highly serviceable in carrying on laboratory experiments of all kinds. For instance, in studying phenomena of impedance, the transformer was removed and a bent copper bar inserted in the terminals. The latter was often replaced by a large circular loop to exhibit inductive effects at a distance or to excite resonance circuits used in various investigations and measurements. A transformer suitable for any desired performance could be readily improvised and attached to the terminals, and in this way much time and labor was saved. Contrary to what might be naturally expected, little trouble was experienced with the contacts, although the currents through them were heavy, namely, proper conditions of resonance existing. The great flow occurs only when the circuit is closed and no destructive arcs can develop. Originally, I employed platinum and iridium tips, but later replaced them by some of meteorite and finally of tungsten. The last have given the best satisfaction, permitting working for hours and days without interruption. Figure 2 illustrates a small oscillator designed for certain specific uses. The underlying idea was to attain great activities during minute intervals of time, each succeeded by a comparatively long period of inaction. With this object, a large self-induction and a quick-acting brake were employed, owing to which arrangement the condenser was charged to a very high potential. Sudden secondary currents and sparks of great volume were thus obtained, eminently suitable for welding thin wires, flashing lamp filaments, igniting explosive mixtures, and kindred applications. The instrument was also adapted for battery use, and in this form was a very effective igniter for gas engines, on which a patent bearing number 609,250 was granted to me August 16, 1898. Figure 3 represents a large oscillator of the first class intended for wireless experiments, production of Röntgen rays, and scientific research in general. It comprises a box containing two condensers of the same capacity on which are supported the charging coil and transformer. The automatic circuit controller, hand switch, and connecting posts are mounted on the front plate of the inductance spool, as is also one of the contact springs. The condenser box is equipped with three terminals, the two external ones serving merely for connection, while the middle one carries a contact bar with a screw for regulating the interval during which the circuit is closed. The vibrating spring itself, the sole function of which is to cause periodic interruptions, can be adjusted in its strength as well as distance from the iron core in the center of the charging coil by four screws visible on the top plate, so that any desired conditions of mechanical control might be secured. The primary coil of the transformer is of copper sheet, and taps are made at suitable points for the purpose of varying at will the number of turns. As in Figure 1, the inductance coil is wound in two sections to adapt the instrument both to 110 and 220 volt circuits, and several secondaries were provided to suit the various wavelengths of the primary. The output was approximately 500 watt with damped waves of about 50,000 cycles per second. For short periods of time, undamped oscillations were produced in screwing the vibrating spring tight against the iron core and separating the contacts by the adjusting screw, which also performed the function of a key. With this oscillator I made a number of important observations, and it was one of the machines exhibited at a lecture before the New York Academy of Sciences in 1897. Figure 4 is a photograph of a type of transformer in every respect similar to the one illustrated in the May 1919 issue of the Electrical Experimenter, to which reference has already been made. It contains the identical essential parts, disposed in like manner, but was specially designed for use on supply circuits of higher tension, from 220 to 500 volts or more. The usual adjustments are made in setting the contact spring and shifting the iron core within the inductance coil up and down by means of two screws. In order to prevent injury through a short circuit, fuses are inserted in the lines. The instrument was photographed in action, generating undamped oscillations from a 220 volt lighting circuit. Figure 5 shows a later form of transformer principally intended to replace Ruhmkorff coils. In this instance, a primary is employed having a much greater number of turns, and the secondary is closely linked with the same. The currents developed in the latter, having a tension of from 10,000 to 30,000 volts, are used to charge condensers and operate an independent high-frequency coil as customary. The controlling mechanism is of somewhat different construction, but the core and contact spring are both adjustable as before. Figure 6 is a small instrument of this type, particularly intended for ozone production or sterilization. It is remarkably efficient for its size and can be connected either to a 110 or 220 volt circuit, direct or alternating, preferably the former. In Figure 7 is shown a photograph of a larger transformer of this kind. The construction and disposition of the parts is as before, but there are two condensers in the box, one of which is connected to the circuit as in the previous cases, while the other is shunt to the primary coil. In this manner, currents of great volume are produced in the latter, and the secondary effects are accordingly magnified. The introduction of an additional tuned circuit secures also other advantages, but the adjustments are rendered more difficult, and for this reason it is desirable to use such an instrument in the production of currents of a definite and unchanging frequency. Figure 8 illustrates a transformer with rotary brake. There are two condensers of the same capacity in the box, which can be connected in series or multiple. The charging inductances are in the form of two long spools upon which are supported the secondary terminals. A small direct current motor, the speed of which can be varied within wide limits, is employed to drive a specially constructed make and break. In other features, the oscillator is like the one illustrated in Figure 3, and its operation will be readily understood from the foregoing. This transformer was used in my wireless experiments, and frequently also for lighting the laboratory by my vacuum tubes, and was likewise exhibited as my lecture before the New York Academy of Sciences above mentioned. Coming now to machines of the second class. Figure 9 shows an oscillatory transformer comprising a condenser and charging inductance enclosed in a box, a transformer and a mercury circuit controller, the latter being of a construction described for the first time in my patent number 609-251 of August 16, 1898. It consists of a motor-driven hollow pulley containing a small quantity of mercury, which is thrown outwardly against the walls of the vessel by centrifugal force and entrains a contact wheel which periodically closes and opens the condenser circuit. By means of adjusting screws above the pulley, the depth of immersion of the vanes and consequently also the duration of each contact can be varied at desire, and thus the intensity of the effects and their character controlled. This form of brake has given thorough satisfaction, working continuously with currents of from 20 to 25 ampere. The number of interruptions is usually from 500 to 1000 per second, but higher frequencies are practicable. The space occupied is about 10 inch by 8 inch by 10 inch, and the output approximately a half kilowatt. In the transformer just described, the brake is exposed to the atmosphere, and slow oxidation in the mercury takes place. This disadvantage is overcome in the instrument shown in Figure 10, which consists of a perforated metal box containing the condenser and charging inductance, and carrying on the top a motor driving the brake, and a transformer. The mercury brake is of a kind to be described and operates on the principle of a jet, which establishes intermittently contact with a rotating wheel in the interior of the pulley. The stationary parts are supported in the vessel on a bar passing through the long hollow shaft of the motor, and a mercury seal is employed to effect hermetic closure of the chamber enclosing the circuit controller. The current is led into the interior of the pulley through two sliding rings on the top, which are in series with the condenser and primary. The exclusion of the oxygen is a decided improvement, the deterioration of the metal and attendant trouble being eliminated and perfect working conditions continuously maintained. Figure 11 is a photograph of a similar oscillator with hermetically enclosed mercury brake. In this machine, the stationary parts of the interrupter in the interior of the pulley were supported on a tube through which was led an insulated wire connecting to one terminal of the brake, while the other was in contact with the vessel. The sliding rings were, in this manner, avoided and the construction simplified. The instrument was designed for oscillations of lower tension and frequency requiring primary currents of comparatively smaller amperage and was used to excite other resonant circuits. Figure 12 shows an improved form of oscillator of the kind described in Figure 10, in which the supporting bar through the hollow motor shaft was done away with, the device pumping the mercury being kept in position by gravity, as will be more fully explained with reference to another figure. Both the capacity of the condenser and primary turns were made variable with the view of producing oscillations of several frequencies. Figure 13 is a photographic view of another form of oscillatory transformer with hermetically sealed mercury interrupter, and Figure 14 diagrams showing the circuit connections and arrangement of parts reproduced from my patent number 609-245 of August 16, 1898, describing this particular device. The condenser, inductance, transformer and circuit controller are disposed as before, but the latter is of different construction, which will be clear from an inspection of Figure 14. The hollow pulley A is secured to a shaft C, which is mounted in a vertical bearing passing through the stationary field magnet D of the motor. In the interior of the vessel is supported, on frictionless bearings, a body H of magnetic material which is surrounded by a dome B in the center of a laminated iron ring, with pole pieces OO wound with energizing coils P. The ring is supported on 4 columns and, when magnetized, keeps the body H in position while the pulley is rotated. The latter is of steel, but the dome is preferably made of German silver burnt black by acid or nickeled. The body H carries a short tube K bent as indicated to catch the fluid as it is whirled around, and project it against the teeth of a wheel fastened to the pulley. This wheel is insulated and contact from it to the external circuit is established through a mercury cup. As the pulley is rapidly rotated, a jet of the fluid is thrown against the wheel, thus making and breaking contact about 1,000 times per second. The instrument works silently and, owing to the absence of all deteriorating agents, keeps continually clean and in perfect condition. The number of interruptions per second may be much greater, however, so as to make the current suitable for wireless telephony and like purposes. A modified form of oscillator is represented in Figures 15 and 16, the former being a photographic view and the latter a diagrammatic illustration showing the arrangement of the interior parts of the controller. In this instance, the shaft B carrying the vessel A is hollow and supports, in frictionless bearings, a spindle J to which is fastened a weight K. Insulated from the latter but mechanically fixed to it is a curved arm L upon which is supported freely rotatable a brake wheel with projections Q. The wheel is in electrical connection with the external circuit through a mercury cup and an insulated plug supported from the top of the pulley. Owing to the inclined position of the motor, the weight K keeps the brake wheel in place by the force of gravity, and as the pulley is rotated, the circuit, including the condenser and primary coil of the transformer, is rapidly made and broken. Figure 17 shows a similar instrument in which, however, the make and break device is a jet of mercury impinging against an insulated toothed wheel carried on an insulated stud in the center of the cover of the pulley as shown. Connection to the condenser circuit is made by brushes bearing on this plug. Figure 18 is a photograph of another transformer with a mercury circuit controller of the wheel type, modified in some features on which it is unnecessary to dwell. These are but a few of the oscillatory transformers I have perfected, and constitute only a small part of my high-frequency apparatus, of which I hope to give a full description when I shall have freed myself of pressing duties at some future date. End of section 14. Recording by Monica MC. End of my Inventions and Other Works of Nikola Tesla. Electrical Experimenter, February to October 1919 by Nikola Tesla.